Okay, so now that we've discussed this in words, let's go through several different mathematical ways of showing that the motion is reproducible and reversible. And so once I get the object flying up and then coming back to the same height, it will have the same velocity that it started with, just the opposite direction. So let's fade away this text so we have someplace to write. So the first thing that we need to do when we discuss these problems is to define a coordinate system. So let's say that we're starting here at some height is equal to 0. And we're going to be traveling upward. So let's choose the positive direction in the vertical direction to be up like that. And so we have two things that get tossed. We have two balls that get tossed off this cliff. I have a ball that's traveling downward with some initial speed. And then I have another ball that's traveling upward with some initial speed. And the question is, when this ball goes up and then comes back down to the same height, what is its speed? Let's call that V final. We want to know what that is. And so if this speed is the same as this speed, then all subsequent motion will be the same because their accelerations and their positions will all be the same. And so that's what we need to show. So there are a couple of different ways to do this. The first way to do this is to look at how long it takes for this projectile that's shot up to reach the top of its motion. And so there are a couple of different ways to do this. One of the things that we know is if I throw something up, when it reaches the top, it stops moving and then comes back down again. So if I compare this velocity here and the velocity to the top, and I know something about the acceleration, I can figure out how long it takes for this part of the motion, just going up and stopping, to happen. So we know that the final velocity is going to be equal to the initial velocity plus the acceleration times time. So here's one of our kinematic equations again. In this case, we know what the acceleration is. It's gravity. But we've defined the positive direction to be up. And so I'm going to give that acceleration a negative sign because it points in the negative y direction or the negative vertical direction. So this is if I rewrite this, I can write this as the original velocity minus the gravitational acceleration times time. Now we also know that the final velocity at the top of the motion is equal to 0. So this gives us an equation we can write out here. So we know that 0 is going to be equal to the initial velocity minus the gravitational acceleration times the time. And so this allows us to solve for how long it takes for the ball to get up to the top and stop. So we can say that t, in that case, is equal to v initial divided by g. And since this is the time it takes us to get to the top of the motion, let's call this t top. So that's the amount of time it takes for the ball to go up and stop. Now, if we look at this motion, here I've got motion under a uniform constant gravitational acceleration. So it's going to take me exactly the same amount of time to get to the top as it does to come back down again, because the motion is exactly reversible. And so this is half the amount of time it takes for the whole thing to happen. And so the total time then, t total, is equal to twice times the amount of time it takes for me to get to the top. And so that's going to be equal to twice the original velocity divided by g. And so we can use that then to figure out something about the motion as we come back down. So let's do that. So this is the total time. So we can use this equation up here again, and we can actually start with the initial speed, and we can use this equation to tell us what the final velocity is at any other time. And so if we use this and calculate what the final velocity is at the total time it takes to go up and come back down, that will tell us what velocity final is right here when that ball comes back to the edge of the cliff. So that says that v final, which is now going to be the velocity at the end of the cliff, is equal to v initial minus g times the total time, times t total. So if I plug in the expression that I just calculated for the time here, then I can write that v final is equal to v initial minus g times this time over here, which is going to be 2 v initial divided by g. And so you can see that magically the g's cancel out here. And so this is equal to minus v initial. And so what that tells me is that when I come back to this place, I started off with a v initial pointing up here. I've gone up and I've come all the way back down, and now at this point v final is equal to minus v initial. So it's equal to exactly the same speed that I had originally, except it's in the opposite direction. And so this then matches the velocity with which I've thrown the ball downward. And so this is one way of showing that at this point, like if I come back to this point, the magnitude of the speed is the same, but I had changed the direction of the velocity. And so these two objects will then travel downward at this point with identical motions, and so they're going to hit the ground at the same speed. Okay, so now let's look at a second way to explore this problem using a different kinematic equation. So we used the equations that relate velocity, acceleration, and time for the first one. Now let's use one that doesn't use time at all, just to be different and throw some variety in here. So we also derived an equation that looks like v final squared is equal to v initial squared plus twice the acceleration times the displacement. That was one of the kinematic equations that we derived. Now we can use this in this situation as well, plugging in a set of accelerations and displacements that are defined by this drawing that we put up here. So we can say that v final squared is equal to v initial squared minus, since the acceleration due to gravity is downward, minus 2g times the change in height. So let's write this as delta y instead, since we usually use y as a vertical variable. Okay, so now that we have that, we can do some calculations. What I'd like to know is how fast is the ball going when it goes all the way up here and comes all the way back down to exactly the same position. So if I look at this equation, what I want to compute is the velocity where I'm back at the same position here. So the displacement is actually 0. And so delta y in this particular example is going to be equal to 0. So this whole term is going to go away. And so what that tells me, sort of trivially, is that the final velocity squared is equal to the initial velocity squared if I don't go anywhere. And so this tells me that the magnitude of the final velocity is equal to the magnitude of the initial velocity. It doesn't tell me anything about the direction like the previous answer did. However, since we know from the drawing that if a ball comes up, it must come down, then clearly that the final velocity here is pointing downward. And so this tells me that the speeds are equal, and we can get the direction just by looking at the picture. So this is another way of showing that when a ball goes up and comes back down to the same height, the speed with which it arrives at the bottom of its trajectory is the same as the speed that it was launched at, except that the direction is changing, so the velocities have the opposite sign. So that's another way of looking at this problem and arriving at the same conclusion that we had before. So a final way of looking at this problem is to actually look at it with distance and velocity versus time graphs. So let's draw a velocity versus time graph for this situation. So if I plot velocity on the vertical axis and time on the horizontal axis, then we can look and see what this motion looks like, and we can make some inferences about how far the projectiles or the balls have traveled and what that does to the initial and final velocities. So we know from our considerations of velocity versus time graphs before that a velocity versus time graph in this particular situation is going to look something like this. I'm going to start off with some initial velocity here, and as the ball goes up in the air, its velocity is going to decrease with constant gravitational acceleration, which is negative in this case. So I start off with some positive velocity, and then the slope of this curve is going to be equal to minus g. So I'm going to have a velocity versus time graph that looks like this. And if I let it continue to fall, it's going to fall forever. So what we can see from looking at this graph is that, so this is halfway through the motion. We called this time t top before, since that was the time at the top of the motion. That's where the velocity goes to 0. And then we can look and see what happens to the rest of this curve. So one of the things that we can say, and we've used this a couple of times now, the area under this curve tells me how far I've traveled. And so this triangle tells me how far I've traveled from starting here at the bottom and going up to the top. And then this triangle here tells me how far I've traveled on the way back down. And so if I come back to the cliff, then it must be true that these two triangles have the same area because I go the same distance up as I come back down again. And if they have the same area, and it's certainly true that the hypotenuse of both of these triangles then has to have the same length because it's from the same line, which tells me that it takes the same amount of time to go from the beginning to the middle and then from the middle to the end. And it also tells me that the vertical distance, the vertical part of the triangle, has to be the same. And so this vertical line here also has length v initial, but it's negative, so this is negative v initial. So by looking at the velocity versus time graph, that tells us that I must reach a point down here where when I get back to the cliff, my final velocity is the negative of the initial velocity that I started at. So that's a final way of looking at this motion and using all the tools that we've developed for kinematics to prove that if I throw the ball up and comes back down again to the same place, it will have the same speed, but the negative velocity since it will have changed direction.